Okay, this video is going to be for the second half of the Calc 3 12.5 lesson. This will cover equations of planes. The previous one covered equations of lines. All right, so a line we know now is defined by one point on the line and then the direction vector for the line, which is in the direction that the line is moving. And so for a plane, we're also going to define that in a similar way. We're going to take a point on the line, and then we have to have something that's like the direction vector for the plane. Okay, but the problem is the direction vector for a plane cannot be in the plane. And the reason for that is that there's an infinite number of possible lines that could be in the plane. So if we want a unique vector that specifies the direction that the plane is oriented in 3D space, we have to use a line that is perpendicular to the plane to define its direction. Okay, and when we do that, that vector is called a normal vector. Okay, so not the same as a normal distribution, but in this context, a normal vector is a vector that is perpendicular to a plane. Okay, and we use direction numbers for it, a, b, and c, just like we did with the direction vector for a line, but in this case, it's the x, y, z components of a vector that's perpendicular to the plane instead of in the path of the line. Okay. All right, so then if we were to define another generic point, x, y, z, that's on this plane somewhere, and then we wrote vectors, a generic vector r that went to there, and then we had a point that we knew was on the plane where we had the x, y, z components p0, and we had an initial position vector r0 there, then similar to what we did with the line, we could define a vector that went from the initial point to the generic point also on the plane. And we would say that this, because I went from the r vector back to here, since r0 plus this vector is equal to r, that means that this vector here would be equivalent to the r vector minus the r0 vector. Okay, so this vector in the plane that goes from our initial known starting point to a generic point p on the plane would be the vector r minus the vector r0. Okay, since we know that that's in the plane, it's definitely going to be perpendicular to the normal vector. Okay, and we know that vectors which are normal have dot products that are 0, right? That's our test for orthogonality. So we know therefore that the normal vector dot the r minus r0 vector has to be 0. And you can even expand that out a little bit and say, using properties of dot products, that n dot r would have to be equal to n dot r0. Okay, now this actually in the book is called the vector equation of the plane. However, we never actually use this structure when we build an equation of a plane. Instead, we go a little further in the definition to come up with a scalar equation of the plane, but it's based on this. Okay, so let me develop what we actually use next. If we start with the fact that n dot r minus r0 has to be 0, and we expand out what those are in terms of their components, the normal vector is abc for its components, the r vector is x, y, z, and the r0 vector is x0, y0, z0. So the difference between these vectors would be x minus x0, y minus y0, z minus z0. Okay, and then if we decided to take the dot product of those two things, that means a times x minus x0 plus b times y minus y0 plus c times z minus z0 would have to be equal to 0. And so if you multiply these out, and then you move all the terms that have the x0s to the right side and keep the terms with the generic x, y, z's on the left side, you get this equation. A times x plus b times y plus c times z equals ax times x0 plus b times y0 plus c times z0. But this structure over here, right, this right here, actually is the dot product of the normal vector and the initial position vector, because if you just took this times this, this dot this, it would be this times this plus this times this plus this times this. So we combine all that together to say that the scalar form of an equation of a plane through point P0 is a times x plus b times y times c times z is equal to a constant on the right-hand side that you find by taking the dot product of the normal vector and the initial point vector. Okay, this is one of the most used equations in Calc 3. We use this very frequently to come up with the equation of a plane. Okay, and it turns out we're going to need to come up with equations of planes a lot. So notice that the left-hand side, the constants are the direction vectors for the normal, the direction of the plane, right? So they don't depend on the particular position, the particular starting point that we give, right? Everything over here is set by the direction vector, the normal. But this number over here depends upon both the direction vector and the initial position. So if we want a plane to be in a particular direction, right? Like maybe we have a bunch of planes here. Let me give an example. And they all are in the same direction. So they all have the same normal vector, right? But I wanted them to go through 3 different initial points. The left-hand side of this equation would be the same for all these planes. The only thing that would change would be the constant on the right-hand side so that it went through a particular point, right? So this number on the right-hand side essentially says where, you know, how far up or down have you oriented this plane in this direction, okay? All right, so best to see this with examples, I think. So let's just look at some examples. Find an equation of a plane. For the plane through this point, the plane has to contain this point, and it has to be perpendicular to this vector. So because it's perpendicular to this vector is in fact the normal vector. That's the normal vector for the plane, which we usually abbreviate with a lowercase n. All right, so now that I have the normal vector, the form for this equation is going to be, we're going to use this, that we're going to fill in this. Ax plus by plus cz equals the normal vector times the initial vector, okay? And so the a, b, and c are just going to come from the normal vector, right, the direction vector. So this is just going to be negative 2x plus 1 times y plus 5 times z equals the normal vector, which I'll write again, negative 2, 1, 5. But then the dot product of that with the position vector, and the position vector will just be the vector whose components are the same as the point that we want to use that's on the plane, so 6, 3, 2. Okay? And so if I do this dot product, it's going to be negative 2 times 6 plus 1 times 3 plus 5 times 2, which turns out to be the number 1. And so the final equation of this plane is negative 2x plus y plus 5z equals 1. This is the equation of that plane. Okay, so really not bad. It sounds worse when you describe it compared to what you have to do, but you have to have a vector that's normal so that you can have your a, b, and c numbers to use as multipliers. And then you have to have 1 point on the plane so you can get an initial point vector to take the dot product to find the constant on the right. Okay, let's take a look at another example. Find an equation of the plane for the plane through this point. So this is my r0 vector, negative 2, 8, 10. But it has to be perpendicular to this line. And they didn't give me the line in the normal form there. They gave it to me as parametric equations. So let's think about that for a second. If I were to pick a couple of different values of t, like let's say, for example, I'm going to do something that I would not normally do. So I'm going to do this in a different color, but I'm going to do this just to justify what I'm going to say that we really will do. Let's pick 2 values of t, okay? And then I'll find the x, y, z components for that. So if I picked 0 for t, I would have the point, let's see, 1, 2, 4, right? I'm plugging 0 in here, here, and here, and getting x is 1, y is, actually, sorry, y would be equal to 0. That would be 0, and z would be equal to 4. And if I plugged 1 in for t, then that would give me 1 plus 1 is 2, and this would be 2, and this would be 4 minus 3 is 1, okay? And so if I wanted to figure a direction vector between these 2 points, if I thought of these as points, right, I could do that by just saying that my direction vector v is going to be the difference here, 2 minus 1 is 1, 2 minus 0 is 2, and 1 minus 4 is negative 3. So I want you to notice that the x, y, z components of the direction vector, they actually just happen to be the multipliers of the parameter here, right? So in fact, I'm not going to really do this. I'm just going to say that if I want to have the equation of a line, okay, or the components of the line, the components of this line are just the multipliers of the parameters. So it's going to be 1, 2, and negative 3. And because this line is perpendicular to our plane, that means this line is our normal vector. And our initial vector is to the point -2, 8, 10. So now I can use the standard form, which is ax plus by plus cz equals n times, or dot, r0. And then for a, b, c, I'm going to use the values of n here. So it's going to be 1 times x plus 2 times y minus 3 times z equals the dot product of 1, 2, -3 with -2, 8, 10, which would be 1 times -2, so that's -2, plus 2 times 8 is 16, plus -3 times 10 is -30, which turns out to be the number, let's see, which one is this? -16. And so the final answer here is x plus 2y minus 3z equals -16. This is the equation of the plane that matches the constraints in the problem. Okay? So if you're given parametric form of an equation, you can get the x, y, z components of the direction along the line by taking the coefficients of the parameter. Okay. And then another example, let's say we want to find an equation for a plane, for the plane that goes through these 3 points. So there's 3 points here. All right. So I can pick one of these points to be my R0. So let's pick this one, kind of has smaller numbers. I'm going to make that one R0. That's the point in the plane that I'm going to use for my position vector. And then I need to have a normal vector, n, okay? But that has to be perpendicular to the plane, but the only thing I have is 2 other points on the plane. So what I could do is I could say if those two, if I think of those 2 position vectors as vectors that are in the plane, so they're in the plane here, I don't know what exact orientation, then my normal vector we could find by taking the cross product of those other 2 vectors. So the way I'm going to find my normal vector is I'm going to take the cross product of the vector of the 2 position vectors 2, -4, 6 and 5, 1, 3. Okay, so for the x, I'm going to be taking the determinant of this little 4x4 matrix. So that's going to be, let me just write it this way, it's -12 minus 6. Don't want to do too much in your head. I'm going to take the negative of the determinant of this and this and this and this. So 2 times 3 is 6. Minus 6 times 5 is 30, right? And then, let's see. For this, we're going to take the determinant 2 times 1 minus -20. So this is going to be -18, right? -18. Let's see, that's going to be, this is 30 minus 6 is 24, but this is -24, but negative of that is +24. And then this would be 22. Okay. So that's one possible normal vector. We could have done it with other combinations of the planes to get to the points, but we would eventually get something which is perpendicular to the plane. And then I'll just complete the process by saying, all right, here's my form. ax plus by plus cz equals n time, or dot product with r0. So this would be -18x plus 24y plus 22z. Those are the a, b, z components from the normal vector. Yeah, unfortunately, I picked a kind of a bad direction because I've got a lot of big numbers here. I've got to do the dot product now of this with 0, 1, 2. Okay, so that's going to be 0 times 18, -18 is 0, plus 1 times 24, plus 2 times 22 is 44. So that would be 68, is that right? Right, so -18x plus 24y plus 22z equals 68. And you know, I could do things like I could divide out, if I don't want these big numbers, I could divide everything by some number. Like dividing everything by 2 would make this -8x plus 12y plus 11z is 34, right? And there are other versions of this that could have, depending on how I did this. So this is not a unique answer, but this is one of the answers. One possible way to do that. Depending on which point I picked for the R0 and which 2 points I picked for the direction vectors, I could get slightly different answers here, but they would all be correct representations of the equation of the plane. All right. So the next thing I want to mention is that I just want to mention this just for completeness, although we don't do a whole lot. We know that the distance between 2 points is given by the 3-dimensional version of the distance formula. Every once in a while, you'll have a situation where you have a plane that's defined in space, let's say, and that you have a point that's not on that plane, and you want to know what is the closest approach distance for that point to the plane. Okay, if you're interested, the textbook has a derivation, or send me an email if you don't have the textbook and I can make a copy of it for you. But basically, without deriving it, you can show that this distance d, the minimum distance of a point not on a plane to a point in a plane, is given by this. It's ax1 plus by1 plus z1 plus d over the square root of a squared plus b squared plus c squared, where the plane is defined by ax plus by plus cz equals negative d, and the point is defined by x1, y1, z1. Okay, very rarely use this, but in case it ever came up, I just wanted to mention it. All right, so that will be it for this second half of 12.5 video.